him. And Joe Venizer was a staff member at Brookhaven National Laboratory and also chair of the physics department there. And T.D. Lee, I don't have to say anything except that he began to be interested in the question of whether one can perturb the vacuum by distributing high energy or density over a relatively large volume. And that sparked, if you like, the field. So many people started thinking about this, and my own laboratory, GSI in Darmstadt, actually, while just being starting the new UNILAC accelerator, actually assembled a group of people. I hope you can read the number of people down here. Some of the names will be very familiar. They assembled a group in 1977 to contemplate new avenues in this area. And I quote here, I have here a slide from the October 16, 1978, where you can see a sketch of what one might want to do to address the topics discussed in Bear Mountain. And you see, in fact, an accelerator here, which is a 12 Tesla meter accelerator now. This has been realized as CIS-18 at GSI, but the rest here, namely a 100 Tesla meter ring, which could also be a storage ring with a possibility for collider mode, was already in the plans. I quote down here that this was actually too big a step for the German and European communities, and only CIS-18 was realized. But we will come to things how they further develop, but you could see that it was already quite important to address these issues very early on. The field really got started by a sequence of conferences, which are now called quark matter conferences. And the first one took place in '79, 5 years after this workshop, after this Bear Mountain workshop. But you see, in the counting of quark matter conferences, this didn't quite make it to be one, so it's called Quark Matter Zero. Then there was another conference in Japan, and the first quark matter conferences were actually two in Bielefeld and at GSI. One focused on theory and one on experiment. Quark Matter 2 actually was in Bielefeld, again, organized by Maurice Jacot and Helmut Satz. And Quark Matter 1983 was a very big conference organized by Tom Ludlam and Harvey Wagner. And I mentioned this here, because it was a defining moment for myself, because I decided at that point to drop everything else I was doing and join the field. And secondly, many, many interesting discussions took place at that meeting, which really resulted in getting the field going experimentally, as you will see. So then it, of course, continued. I don't want to go through this. We are actually now at Quark Matter 29 in October 21 is planned. So you see there 28 Quark Matter conferences have already taken place, and you see here the list. The rest you can find on the web. And I will not dwell on this any further. Share a few slides from some of these meetings. This is meeting in Bielefeld 1980 with T.D. Lee and Migdal and Gordon Baim in the background and Helmut Satz here. An important political part was that this quark matter research had to find its entryway into the political circles who decided on the money, so to say. And so right from the beginning, even though this Quark Matter 3 conference in Brookhaven was essentially half-half high energy and nuclear physics, the discussion which followed centered the field, the new field, quite solidly into nuclear physics. And so under the auspices of that, there was a Nuclear Science Advisory Committee meeting in 1983, where plans were first actually drawn out to build a big accelerator. And you can see here the list of people who were on it, and Gordon Bame's handwriting is difficult to read here, but you should just see that it has to do nuclear matter, the fundamental material of nuclei. And a consequence of this Quark Matter 3 1983 international conference was that a task force was formed to further this system, and this task force was then followed by a RIC technical committee, a RIC review board, and eventually by the RIC policy committee. And this is where all the decisions were made to build a dedicated accelerator, namely RIC. You all know that RIC actually started to run in 2000. So about 17 years after the task force started and after QM3, but it started and it produced a lot of nice results. I show you here the RIC Advisory Committee, and you can read some of the names. Hermann Feschbach here, Gordon Bame, Nick Samios, Rudolf Bock, and I will not read them all now because I do not have time, but you can look through the slides and see them all. Now, during that time, also the first ideas for fixed target program, so to say, on the way to the RIC collider was drawn up both for the HGS at Brookhaven and the CERN SPS, and that one went extremely rapidly. So 1983, as I will show, the first mention of a fixed target program. 1986, the first oxygen and silicon beams, actually was silicon beams at Brookhaven in 1986, and then also the first oxygen and sulfur beams. So in 3 years, not only were these beams produced, but also the experimentalists got experiments together to do some very meaningful experiments. And in 1987, at that Quark Matter conference in Nordkirchen in Germany, the first results were shown. I will not go into the details of how RIC was built because Gordon Bame wrote an article which you can find here and gave a talk at Quark Matter 2015, and I have not much to add, so I will just continue. A panel discussion at Quark Matter 1983 was very influential, and you see here Björkén, BJ, you see Miklos Gyulashi, you see Arthur Schwarzschild, who you may not all know, and Reinhard Stock, and Alan Bromley as the chair. And that panel discussion sparked the interest of many people. And for example, Arthur Schwarzschild, on the occasion of that panel, then chair of the BNL physics department, described the program for heavy ion physics at BNL within 2 years, actually it took 3 years, to inject heavy ions directly from the tandem Van de Graaff accelerator into the HGS. And this was a plan which was realized quickly, and I have to say also quite strongly supported by the agencies. And the idea was to build a constituency for collider experiments that should lead to collaborative efforts between nuclear and particle physics, providing an appropriate arena and stimulus for detector development necessary for collider experiments. And as Schwarzschild put it, new physics calls for a marriage between nuclear and high energy, and this conference looks like an engagement party to me. Actually, it turned out only halfway like that, because in the end, when really the big detectors were built, they were built mostly by nuclear physicists. Although particle physicists really helped on the way. Now, Reinhard Stock was the driving force behind the CERN fixed target and collider program. And he described the experiments and argued that one should make use of existing equipment and concluded that the development of new detector technology would indeed be required for collider experiments. And that turned out to be really true. So on that way, there was the beginning of the program with ultra-relativistic nuclear beams at CERN. And I show you here a letter from a list of mostly or all German experimentalists to the CERN management. Herwig Schopper was then the DG, and Professor Klapisch was the research director. And in there, they proposed to use heavy ion beams in the SPS. And this was actually accepted. And within, of course, in order to do that, important components had to be developed. And in particular, the RFQ was developed between Italy and Berkeley. And the LINAC with a new IH structure came from GSI. And I think the ECR source came from France. And you see that was an international effort to get the injector for heavy ions to CERN. And it was only because of these connections between different laboratories that this program really took off. So I make now big jumps. The experimental database until about 10 years ago, that is from 1986 to 2010, led to an impressive experimental database from 1986 to 2002 at the HES and to on the SPS from 1986 on. Actually, SPS is still ongoing. We have still Na61 as a heavy ion experiment at the SPS. And at all energies, production yields of particles were measured for practically all stable or weakly decaying hadrons. And this led to many important results which are listed here. Fireball produces particles in near TC in chemical equilibrium, strong collective expansion, jet suppression, low mass lepton pairs, anomalous germanium production. And I put this in quotes because this is the one thing from all this list where we now have a totally different view on things here compared to what it was in the beginning. And I will come back to that. After about 14 years of experimenting with nuclear beams in the SPS, CERN made a press release, evidence for a new state of matter in January 2000. The summary of this was given by Ulrich Heinz and Maurice Jacot, and you can read it in this archive number. And it says essentially a new state of matter was found in heavy ion collisions at the SPS that features many of the characteristics of the theoretically predicted quark-gluon plasma. So it just stopped short saying that we have discovered a quark-gluon plasma, but essentially many of the characteristics of that state were found in the first decade of experiments. And of course, now let me go on and discuss a bit of physics. And of course, I have to be very selective. And we have 3 talks following my talk where many things will be discussed in more detail. So I will actually concentrate only on 2 examples, which are listed here. But I would like to point you to 2 recent reviews, one in 2016 in Physics Reports and one in Annual Reviews of Nuclear and Particle Science in 2018, where many of the important topics are discussed in great detail. So what I would like to do is in the next 10 minutes or so, before I look into the future, I would like to discuss two topics only: statistical hadronization of quarks, and I mean with quarks up, down, strange, and charm. The bottom quark I will leave out, and the top quark plays essentially, at least up to now, no role in heavy ion research, even though it has been seen in lead-lead collisions at the LHC. And the second topic is, and I will also be very brief there, but update you on the most recent results from a search for possible critical endpoint in the QCD phase diagram. So UDS hadrons, so we leave the charm out first, and the QGP phase boundary. What is this? So all the experiments that have been mounted at the HES, SPS, and finally at the LHC actually measured hadron production and tried to measure and identify the hadrons over a wide part of phase space. The final result of that was done over the last 8 years by the ELISE experiment, and the data are collected here. You can, for example, look here. The upshot is really quite surprising. What I show here is the yield of hadrons per unit rapidity, measured at mid rapidity, that is rapidity 0 in the center of mass system. And the yield of these hadrons is plotted here for very many different hadron species, from pions to kaons, phi mesons, protons, antiprotons, lambdas, cascades, omegas, and their antiparticles, deuterons, helium-3 and their antiparticles, hypertriton, anti-helium-3, helium-3 and helium-4, and so on. And these yields can be precisely, and you can see here by which the data differs from what I'm calling now statistical hadronization. These yields can be precisely measured with a statistical operator that essentially represents QCD at or very near the phase boundary between hadronic matter and quark-gluon matter. Let me first say at LHC that matter and antimatter is formed in equal portions. You see here, essentially particles and antiparticles have the same yields. In fact, we have tried to measure a difference, did not succeed, but we have a very small baryon chemical potential from this analysis. As you can see, 0.7 MeV, but the uncertainty is nearly 4 MeV, but that is already very good. The global common temperature representing all this state, this thermal state of hadrons is 156.6 MeV. And in order to actually obtain this really beautiful agreement over 9 orders of magnitudes, one had to go and introduce the full slate of hadrons from the PDG, nota bene, hadrons with their masses at t equals to 0. And when had also to take into account interaction among these hadrons by making an S-matrix treatment of their interaction, making use of the 40 years of hadronic physics the community has gotten over in the last 40 years. And this result here tells you that one has a very detailed description of hadron production. In fact, one can do this for all beam energies where this has been measured. And this now has, in fact, a predictive power such that we can predict, for example, at any future collider, like the future circular collider, within, let's say, an accuracy of 10%, the production of omega baryons, the production yields of omega baryons. And I think anything but that yield would be a very big surprise. So one can plot, I should say, at each point, At each energy where such measurements have been done, you obtain a pair of values from the analysis, and the temperature and the baryochemical potential. And you can plot that into a diagram, which we call the phase diagram of QGP or QCD. And you see all of the world's data points here. In fact, each of these data points essentially represents an experiment. And all of these data points have been assembled by practically all of the collaborations working in the field. This is really working together over 30 or so years. And you see that we get something which is actually very close to where lattice QCD results represented in these two collaborations predicts where the phase boundary should be and even what the phase boundary should be, for example, crossover or not, even though we have no experimental confirmation of that. So we have actually from all of these measurements a very good idea about the QCD phase diagram, albeit in an area over a very wide range, much wider than any theoretical predictions exist. And what is most surprising is that actually the experimental determination of the phase boundary at mu equals to 0 coincides precisely with the predictions from lattice, as you can see here. Now, how about the charm quark? The charm quark is much heavier than the temperature which comes out here, which is something like 156 MeV. The charm quark is more than a GeV in mass, depending on scale. So the charm quark should not, and that most people thought should not participate in all of that, but that turned out to be wrong. Before that was realized that it is wrong, there was an idea, namely to implant charmonia into the QGP and observe their modification by so-called sequential melting or suppression in the QGP. Famous paper by Matsui and Satz, more than 3,000 citations by now. But we realized about 20 years ago, pretty much exactly 20 years ago, that if the QGP screens all charmonia, but charmonium production takes place as all the other hadrons also at the phase boundary, then one should expect not suppression of charmonia, but in fact enhancement of charmonia compared to at colliders, compared to what one would do if this component does not exist. This has been reviewed here, and it is I come to the next. It is sketched essentially here. The nuclear modification factor, that is the number of charmonia expected if one only has few charm quarks in the system, should, with a function of the centrality or the number of nucleons in a collision, actually go down. But if one moves, and this is for the Wick energy, but if one would go to LHC energy, you should actually see something which is significantly higher, not lower, as was predicted by the Satz model. And the first data at LHC immediately showed that that is actually what is realized. The blue data are from Wick, same RAA. The red data from LHC, the energy has been increased by an order of magnitude. The energy density has gone up significantly, but the shape size do not go down from the blue line, but go up. So that was a very first important discovery at LHC. And incidentally, as explained in detail in this Nature paper here, this is the first and direct proof of deconfinement for charm quarks. You can see this now in much more detail. This is the newest, or pretty much the newest data we have in ALICE. And you see here how this RAA actually starts to increase as one goes to more and more central collisions. And we see as a function of transverse momentum that actually RAA now reaches or even exceeds a little bit 1. So you really see enhancements directly. Now, this has been accompanied by a very serious effort from the various lattice groups. Essentially, I show here a result from Bielefeld, BNL, and Wuhan lattice group, also called hot QCD. And they have managed, this is very new result from this year, they have managed to trace the fate of germanium in hot matter and realized that actually there is no evidence from this lattice calculations of survival of germanium bound states beyond TC. This is a big change from what lattice was predicting even 5 years ago. But quite consistent with this picture of statistical hadronization, which I showed you in the previous slide. And even botamonium, you have to have some fantasy. For 1.5 TC, there is essentially nothing left. Sorry. I need to go back. Even botamonium, I think there the final story is not yet set because botamonium is so small that it's hard to compute that on lattice, but even there is not much living alive in the QGB. So one can actually extend the statistical hadronization for open and hidden charm, and actually it should work for all charmed hadrons. And I show you here what happens if we do nothing more than the same model we had before and compute the transverse momentum distribution for D mesons. There's no free parameter. We use the same charm cross-section, which we need as before. And you see that it actually works very nicely. And if you plot in this thermal plot where now we have the yields per degree of freedom versus the mass of particles, where all the hadrons line up nicely. If you plot in that shape psi, you realize that it is outside of this thermal line here, this blue dashed line, by roughly a factor of 1,000. And that, of course, finds its simple explanation that the enhancement which you should get, sorry, the enhancement which you should get from the charmed quarks, because there are many more charmed quarks due to hard collisions in the fireball. And if they thermalize, then there is a real enhanced population of charmed quarks that is 30 per species of charmed quarks. And since you need 2 in the shape psi, it's 30 squared. So that is exactly this factor from here to here. So this quantitative agreement for open and hidden charm hadrons implies that there should be rather dramatic effects as one goes to more and more exotic hadrons. And for example, omega CCC with 3 charm quarks should have an enhancement factor of about 30,000. So we look forward to seeing that in 1, 3, and 4, and maybe beyond. The last 2 minutes, search for critical endpoint in the QCD phase diagram. If the phase transition is crossover at 0 mu b and it is first order at very high baryon density, then there must be a critical endpoint between. And various people have studied this and argued that if one gets close to this critical point, there should be critical fluctuations, which we could measure by moments of net baryons. I show you the final result of this. This is a very difficult measurement, which was pioneered by the STAR collaboration that measured up to the 6th moment. The results are in here. And in fact, the data points are these plaque points here. And as a function of root S from 60 to 7.7, so it was already a tier of force to go down in collider energy to 7.7. The red line is what we have concluded should be the baseline if there are no other effects than essentially hadron resonance gas and baryon number conservation. And we made a statistical test, and that line here, given the unfortunately still large uncertainties in the data, implies there's only a 1.5 sigma significance for non-monotonic or possibly critical behavior in the data. So we have no evidence yet for a critical point, but of course we all look forward to much improved data from the Weak beam energy scan too. And a few comments on the future programs. In the high baryon density region, we now have a very large number of different projects. You see here CIS 100, that is the FAIR project with CBM and HADES. You see NICA, which of course will be at Dubna, an important collider. Of course, RIC is participating. The SPS will still continue, and there are projects in China and in Japan, and on the way, of course, also further in Dubna. And all of these projects are, apart from the SPS, are still in the construction phase, but we look forward to very interesting results from this program. And a couple of words on LHC. You see here the overall timeline. We are here at the moment, somewhere shortly before the end of this long shutdown 2. And that will start LHC 1.3, which will get results from PP to PLED to LED-LED with a full program. And you can see here that LHC 1.4 should start in 2027, and maybe now it actually is conclusive. They're concluded that in 2032, the heavy ion program will continue at the LHC with a full PP, PA, and ion program. And you can see here, while in run 1 and 2, we had only one inverse nanoband of LED-LED collisions. In run 3, this will be increased by an order of magnitude with detector upgrades for practically all detectors in the ALICE detector, and also with strong participation by LHCb and Atlas and CMS. And I conclude with the final slide, next generation. I don't know why this is shifted here, but okay. Final slide, next generation heavy ion detectors for LHC 1.5 and 6, and a fast and ultra thin detector with precise tracking timing with another factor of 50 compared to what we now get in luminosity increase, and with ultra thin silicon, even curved, and multiply heavy flavor production, multi-quarks, that's chiral symmetry restoration, and phase at particular, oops, what did I do?
You can click on
okay.
back, and then you will.
Yeah, I go back to the end, and then I can also even get this in a bit better. Oops. What is this? Okay, so the final, let me put this on slideshow. So, this is, sorry, I have to go back to this. This was a mistake. Anyway, I think the final part of that will be test of fundamental properties of quantum field theories for very soft photons and new physics in the soft sector. And this will keep the heavy ion program going if all these plans are realized well into the 30s, even beyond for the next enterprise and exploration of heavy ion physics at the highest energies. Thank you.
Thank you very much, Peter, for this great overview. So the floor is open for questions.
Hello, I just posted a question in the chat, but I can ask it.
Yeah, please.
My question is that when people discussed in these meetings, historical meetings about PP colliders, they typically thought about the physics of the terascale, and they thought about energies that would let the physicists access the physics at the terascale. Were there similar discussions in the heavy ion community and the quark matter community? Was there an energy scale that people decided would be the energy scale, or was it all driven by what was possible at the time?
No, so indeed, there was a very detailed discussion. I didn't have time to go into these details. You have, of course, when you collide ions, there is, in order to get energy density at mid rapidity, you have to slow down and destroy the nucleons in the two beams. And this phenomenon leads to two separate regions, namely the fragmentation regions, where the beams, the remnants of the beams are situated, and the central region where the essentially baryon-free area is obtained. And early on, even in 1983, it was estimated that in order to find a baryon-free central region where this fragmentation region doesn't overlap with the central region, one needs to go beyond 50 GeV per nucleon. The RIG collider then was built at 100 GeV for each of the beams, 100 GeV per nucleon. And as you all know, the LHC is in the GeV per nucleon. And we already realize now that the central region is baryon-free to much better than 1% at LHC. I hope that answers your question.
Yes, thank you for the very clear answer.
Okay, other questions to Peter? If you don't mind, I just probably a quick question from my side. What would be the most interesting part? I mean, since you have already mentioned that at high energy is a baryon-free regime, so what would be the most interesting for the top LHC energies? What will be the most interesting probes for this high energy frontier?
Well, you can already see here, this is why I brought up this line. What we actually want to do in 1.3 and 1.4 is study further light flavor hadrons, including the very surprising facts that we can produce precisely as prescribed in this statistical hadronization scheme. We can produce very loosely bound objects like deuterons or hypertritons, where the total binding energy of a hypertriton is a bound state of proton, neutron, and lambda is only 2.5 or 2.3 MeV, and the lambda is actually bound only by 100 or 150 keV. And yet you can produce it with significant rates in TeV collisions. But of course, we want to also go and study further these quarkonia, where we have already seen that we can see directly a deconfinement of charm quarks towards exotica. And then an important topic at the LHC is jets. I didn't have time, but Marco von Leben, who will come soon, will actually focus on that, and you will see what one can get from jets. That is a very important and interesting area. And of course, low mass leptons and real photons get us insight into the system because these photons come out of this dense system. And actually, there are many topics which have nothing to do with quark-gluon plasma, but ultra-peripheral correlations and hadron interactions from correlations is another important topic for the next decade.
Okay, thank you.
Maybe let me ask one if I could, Gregory.
Yeah, sure.
So every once in a while, not very nice talk, Peter, thank you. Every once in a while, there's an idea of a new machine, super LHC or something like this, that go to higher energy. And almost inevitably, when I hear talk about that, or at least I used to, one would say, well, could we put heavy ions in that machine? And I guess the question is, if there would be a machine that would be 10 times more energy, root S, than LHC, would it be a natural thing to say, okay, we should definitely start a heavy ion program there, or is that something that is not so obviously worthwhile?
Well, of course, we've thought about that, and that's all people before, when the new energy area became feasible to think about. And there is actually, if you go and have a look, there is a paper on the server about heavy ion physics at the FCC, at the Future Circular Collider, where all these areas are investigated and discussed. There's very clearly areas where you would dramatically benefit from the energy. And let me start from the beginning, from the bottom here. In ultra-peripheral collisions, then of course the kick a nucleus gets from the photon field will be essentially scaled like gamma or gamma squared, and you get a huge production of, for example, epsilon mesons and so on, and you could see things like saturation physics and so on in all great detail. We already have very interesting results in this area. Now, the main point which will be different if you go to super LHC or FCC would be that there is so much charm production that this becomes actually a significant, still small, but significant fraction of the fireball. And that would mean that you should really see a quite substantial production, very significant production of exotic hadrons, of JPSI and so on in very interesting quantities. And that is really one of the major points, but it is also clear that essentially, as I said before, we believe we can predict hadron production at any energy, including FCC, that if these predictions are right, you certainly would not build a collider for that. But if it is being built, we certainly would love to check it.